All right, we'll get started. First of all, thank you all for being here today for this very special joint RAL and CGD seminar. And I know a lot of people are online too, so welcome. Very happy to introduce from Colorado State University, the Department of Atmospheric Science, Dr. Elizabeth Barnes. Also goes by Libby, a professor there and soon to be a professor at Boston University. And so, I know Libby's familiar to a lot of the folks here through collaborations and various organizations. Just a couple to name a few is the NCAR Earth System Predictability Across Timescales, part of the External Advisory Board, and also part of the NSF AI Institute for Research on Trustworthy AI in Weather and Climate and Coastal Oceanography. So perhaps you've collaborated with her through those channels or others. Just a little background, bachelor's in both mathematics and physics in 2007 from the University of Minnesota, and also the PhD following that in atmospheric science in 2012 at the University of Washington. So Libby does work based on what I've seen across a really broad cross-section of the field in climate science, atmospheric science, Earth system predictability dynamics, and has most recently become well known for her innovative work in machine learning and AI, which she'll be talking about today. Looking at Google Scholar, it's mentioned over 100 publications with over 10,000 citations, so very impressive. And one piece of trivia I think I learned through a previous talk is you've done some work with your father, Randall Barnes, who's a professor at the University of Minnesota. Both her parents are civil engineers. And finally, just some notable accolades of, and this is just a small number of many. She recently was awarded the Presidential Early Career Award for Scientists and Engineers earlier this year, awarded by President Biden. She's a fellow of the AGU and has also earned the AGU Massillwain Medal and the AMS Clarence Leroy Messenger Award, along with an NSF Career Award. I'll stop there and I'll turn it over to Libby.
Okay, thank you everybody for being here. This should be fun, I hope. We can all use some fun right now. All right, so I'm going to talk about our machine learning work we've been doing in my group. In terms of timescales, we work across many timescales. I even work on the weather timescale now, which used to be crazy to me. But today I'm going to focus more on the climate side of things. But for this diverse audience, I want to point out the goal is not necessarily for you to come away with all the climate knowledge, but really just how we're using these tools to address our science questions. And my hope is at the end, you might be inspired if you don't use machine learning already to maybe take a look at how it could or could not be useful for your own work. So that's the goal. A roadmap, so I'll do just a brief overview from my perspective of AI applications in weather and climate to date. There are many. We've been talking about this area for 5-8 years now, many of us, but it's still nice to talk about the landscape. Then I'll go into our use of explainable AI for climate prediction specifically across timescales. We'll start at the long timescales and zoom in. And then at the end, I want to talk a bit about using XAI to anticipate these human Earth system features. All right, so so just as a point of reference, if you've seen me give a talk before, I show a figure like this all the time because I really like to point out to people, I really do love tools, to be clear. I love methods. I could get excited about talking about metrics all day, but it is still a tool and it's not the only tool. And sadly, there are times when I have to tell my students, in fact, machine learning is not the right tool, and linear regression or something very simple like compositing, or what I call fancy averaging, will do just fine, okay? Our idea here, though, is when machine learning is the right tool, how do we use it to really take our noisy, complex system, that is the Earth system, and use it to actually make predictions about the real world? So there are a lot of applications right now for AI. You've likely seen things such as this. So thinking about severe hazard forecasts and trying to make or replicate certain products coming out of NOAA, can we do them potentially faster with machine learning algorithms? So you can think of this as a single learning task. I want to do one specific thing. We've seen AI for post-processing. I've had multiple conversations today already about using AI for not just downscaling, but you can also think compression, something I'm really excited about, and doing corrections. That could be bias corrections, but also as you downscaling doing certain post-processing error correction. This is where, in my view, the climate field really started, which was thinking about machine learning to make our models better through better parameterizations. This is an old figure now, but still many folks are working on how do we make our weather and climate models or Earth system models better with machine learning. Something that's not talked about as much or accentuated, but I think is incredibly powerful, is merging observations and model data together to get the best of both worlds. You might say, well, that sounds a lot like, say, data assimilation. Yes, indeed. People have been doing this for decades. But what machine learning allows is for people across many disciplines to start merging model and observation data, or their own model and observation data with other disciplines' model and observation data to try and get the full pipeline, which to date, I think in our system prediction has been incredibly challenging. How are the hydrologists talking to the city planners who are also supposed to be talking to the atmospheric scientists and oceanographers? Machine learning is allowing us a platform to sort of combine everything together. So I really, in my view, looking forward, when we look back and write some review paper in 10 to 20 years, I actually think this is going to be a huge topic in those articles. You can come find me in 10 to 20 years and tell me how I did. Okay, climate change communication and visualization, right? So the bottom picture has been around for a long time. The top one's quite new. And the idea is using generative AI to try to visualize what a location may look like under certain kinds of climate hazards, in this case on the top, in both cases flooding. And then finally, we get to deep learning weather and climate emulators. Yes, these can fall into the other categories, but I really like to point out they are a bit special because they're really these fully data-driven models of our system. And they are representing extremely exciting opportunities as well as challenges that I would argue the scientific community is poised to address. So one example is papers coming out in Nature in the last few years about global weather forecasting, and then many other papers. These are all a few months outdated, but I just like to make the point that there are many of them. And actually, my PhD student compiled a list. This is from the last half of 2024 of the papers that came out with emulators. And there's a list for the first half of 2024. There's a list for 2023, of course. And there's also the 2025 list. So the point is, these are everywhere. What they're all good for, we have to figure out. Are they, do we only need one to rule them all? Do they all have their special applications? And these are the sorts of questions that I think, again, the science community, we can help figure this out. So why would we use AI? Just as a reminder, if you see my talks, you know my answers, but to do something faster or cheaper. And sometimes people look at me like, well, that's not really science, right? Like just faster or cheaper. I want to learn something. I get it. But often to learn, we want to be able to do the simulations or do that test, that hypothesis test, in enough time that our graduate students can actually get their degree, right? And so doing something faster and cheaper really is about allowing us to do the science that we want to do. There's also the ability to do something better. So even if you can't do it better, even if it's about the same as what you were doing already, but you can do it 100 times faster, well, now you can do 100 more somethings. And I think both of these are key to why AI has taken off in our field the way it has. And then finally, learning something new, which I will try to highlight today. It's not only these top two. The bottom one is certainly an exciting frontier as well. Although I have found that, at least in my experience, machine learning is just another tool to help us learn something new. And that if I brought up linear regression or principal component analysis or Fourier analysis, those are also tools allowing us to learn something new. This is just another one. Okay, so my group, what we do is we try and develop and implement AI tools to leverage imperfect models in support of Earth system prediction. And this is where I really want to emphasize how important climate and weather models are in our work, especially at this point, physics-based models upon which many of these are trained. And then finally, what the types of questions we're asking is when, where, and how are environmental conditions predictable? And just to give credit where credit is due, this is my awesome group as of last fall, and I'm gonna circle their faces in pink just so you know what wonderful people are actually doing a lot of this work here. All right, so I told you we're gonna start long time scale and then zoom in throughout the talk. So we're gonna talk about that longer time scale, thinking about how long we might have until critical warming thresholds are reached. So we know, globe is warming and people talk about these specific thresholds. Now, to be clear, there's nothing necessarily special about these thresholds, but they give us something to put our narrative around, right, to talk about. And the important point here is the question marks on the bottom is when will we reach these points? There's a lot of talk right now, also about 1.5 in the last year, right? And one of the questions is, how long do we have to wait till 3 degrees? And you could say, well, let's just look at climate models, but climate models differ in their answers to this question. So depending on which climate scenario you're on, which climate model shown in colors that you're using, you pass these thresholds at different points. And as a field, we already do processing of the different models to try and find the best, sort of the best real life answer or the best answer we think for reality. And I'm gonna talk through how we're using machine learning to do that as well. So this paper came out in 2023, and we just recently published an update to it for regional predictions. So I'm gonna start with the global, and then we'll zoom in on the more regional picture. So what we did, and this is in collaboration with Noah Diffenbot at Stanford, we make a great team. He loves downloading data and regridding and processing it, which makes no sense to me. And I love writing code and training machine learning algorithms. So together we are quite the pair. So here's the idea. We input a map, so we take from a climate model a single annual mean, say, surface temperature map for a particular year, and we train a neural network to predict how many more years from that snapshot, that particular simulation will reach, say, 3 degrees. So how many more years does this world right now have left? Now you can imagine as we get closer to 3 degrees, there will be fewer years until 3 degrees. We can do this over many climate models and train over many climate models at the same time. So it starts to learn patterns to look for that are common across many different simulations. Now, we don't just predict the actual number, like 33 years. We actually predict parameters of a distribution. So in this case, this is a Shash distribution, but you can imagine it's like predicting the mean and the standard deviation of a distribution. So we can actually get a certain amount of uncertainty, and some of that uncertainty will come from lack of training data. It will also come from the fact that climate models differ, and that will be what we call encoded in that answer. Okay, so how does it do? This is actually sort of the boring part, but the true number of years is on the X and the predicted number of years on the Y. So this is our testing set, and you want the blue dots and the gray dots to be along the one-to-one. They mostly are, it looks fine. This is just saying that it worked, and it was able to generally learn this relationship from these maps. Okay, this is not the interesting part, because in essence what I'm having it do, to give or take, is predict something I already know, because I could have just looked at the climate model and said, when does this line cross 3 degrees or 2 degrees or 1.5? That's not interesting. The more interesting part is now that we've trained it over many climate models, now we can freeze what we call freeze those weights and instead input maps from the real world. And we can ask, okay, you haven't seen this climate model before, but given these maps, how long do you think this world has until we hit these thresholds? So in this case, this is from the Berkeley Earth surface temperature data set, and these are different maps from the observations of different years, and we can put those years in and say, how long do we have until 3 degrees if you assume a certain scenario, climate change scenario? So we've done this. And you can make a plot of, for every year's map you put in of observation, how many years until it thinks we're gonna hit 2 degrees C. So a few things to note. First of all, if it were a perfect prediction, one of the things we'd expect is every year we should step 1 year closer to the right answer, right? That slope should be -1. They're not always exactly -1. In this particular case, it turned out it was, but it could be 0.99 or something like that, years per year. So that's promising. That gives us some confidence that it's learning something right. Now you might say, hold on a second, that you only fit that dashed line at the end there. I see what you did. We're not trying to be shady here. Actually, you'll notice there's a bump, right? And this bump is actually Pinatubo erupting. And so what happened is that these maps, it's actually cooler than normal because of the volcanic aerosols. And so because of that, the network sees it and thinks, oh, we must be further in the past. We have a long way to go before we hit 2 degrees, which is wrong. But actually, it's the kind of wrong I sort of like, because I never really tried to train it to learn about volcanic aerosols. Just a few years later, it gets back on track when those aerosols are deposited. All right, so using this, we can make a prediction and talk about how many years in the real world do we have until we hit these different thresholds, and then we can put some curves and uncertainties on it. And the big point here is not necessarily the numbers, but that we got a higher likelihood of reaching 2 degrees in the low scenario than other previous assessments have. So that we did this for the global picture, but regionally we might be more interested in what's going to happen on a regional scale. And so we repeated this study that just came out in December, where we did this for all of the IPCC regions separately. So how long does the Central North America region have until some threshold? But we went a little further than this because we started seeing there are large climate model biases that are regional that actually start to pop out significantly. So what we do is we do something called transfer learning, where we train on climate model data, like I just explained. So same exact setup, made the writing the code easy, right? And we could just predict observations, which is what we just did. Or instead, we could train on climate model data and then fine tune with the limited observations that we have, because we've already warmed in many of these locations already. We can learn from that. And so in this case, we learn about thresholds like 0.8C, 1C, and 1.2C in those different regions. In this way, the network's able to update itself to be more relevant to the real world because it's actually been able to train and see observations. So I'll show you what this does. With our particular architecture here, we're actually able to make time series of predictions now rather than a single threshold. So on the x-axis is year, and on the y-axis is temperature anomaly. The gray is all the different CMIP6 projections that we have. The black is observations. The teal base network is what we got when we didn't do this transfer learning step. And the orange is what we got when we fine-tuned on just 3 different data points. If you care, they're the ones shown in circles. And what it does is allow us to do this very crude, if you will, bias correction to ensure that we can have an even more relevant prediction for the real world. All right, so we did this for all these regions. Please don't stare at this too closely. However, we can start to talk about which regions did that transfer learning process make a difference. That is, where did potential climate model biases actually get in the way, and transfer learning actually allowed it to update it. Also, what we were looking for is, does this process further constrain our projections? Because if we get the same give or take prediction with the same uncertainty as we would with CMIP6 as a whole, what was the point? The whole hope is that we'll have a better prediction of what the real world or what the future holds than we would have gotten from the ensemble spread and the ensemble mean of the CMIP6 data set. And so the take home here is that machine learning with this fine tuning significantly constrained our projections. These curves are thinner than the gray bars from all of CMIP6. And it's suggesting that thresholds, unfortunately, will occur sooner than anticipated from earlier studies. Okay, so now the window part. So how did the network make its prediction? One of the questions is, how is it able to do this transfer learning process? Where is it updating its knowledge when it sees the real world after we've trained on climate models? And we can use these explainable AI approaches. There are many papers now on these topics specifically for our field, so I encourage you to check them out. The computer science literature it's massive on this topic and changing every day. And I actually find that now there are dozens of papers from earth scientists on explainable AI techniques, so I highly encourage you to start there if you're interested. For those unfamiliar, I'm going to come back to my cat example. This one has come with me since I think like 2019. So I'm going to show you some plots that are called attribution heat maps that allow us to look at the regions of the input that are most relevant to the prediction. So when we ask, how did it come to that prediction? Where was it looking? It can create a heat map to show us generally the most important regions of that input. In this case, it's a neural network predicting the probability of there being a cat. So you look at the image and it says, oh, it's a 0.8 value for the cat, and you can propagate that backwards with these XAI techniques and get a heat map that looks like the input that highlights the regions relevant for the decision of a cat. And this is where people go, but it's where the cat is. And I say, yes, it is, which makes you feel like it's working. And actually, one of the problems is in earth science, we don't actually know where it should be working, so we don't know how to tell if the XAI method's working at all. Whereas in many computer science applications, they're using cats and dogs, and they say, hey, it's sort of around the cat head, and that makes sense, so it's fine. That's a different challenge for another day. Okay, so anyway, so these are the sorts of maps we can make, but instead of cats, we can use pictures of the globe, of surface temperature, of precipitation, et cetera. I will point out, why would you use explainable AI? For this audience, you're, I think, a friendly audience, hopefully. Many of you probably are scientists and saying, well, because I care why. Like, enough said, I don't need you to give me this slide. But I'm going to give it to you anyway, because you might be surprised when you leave the academic or the science community how, for many people, that will not fly. They need something beyond just curiosity for why you would use and want to understand how machine learning is making its prediction. And I've run into this many, many times now. So even if you don't care why, you should still care. We need to gauge trust, right? We need to know, should we blatantly believe the numbers being output here? And the answer is probably not. And XAI helps us understand that decision making. We've used it many times now to fine tune and optimize our networks. So it's not working very well, and we need to figure out how to fix it. Well, one of the first steps in fixing it is figuring out what it's doing wrong, right? And how and why it's doing it wrong. So understanding that decision-making process allows us then to go, oh, I see, it's focused on the sea ice, which was not what we wanted. This just happened last week. I don't want it to look at the sea ice. That's not part of my science problem, so we just chopped out the poles, okay? Problem solved. So that allows us to do that fine-tuning. And then finally, we can maybe learn something new, like, oh, why is it looking there? Let's go investigate that further. So it's really a hypothesis generator in many ways. Okay. And this is my caveat about causality. Our goal is to understand why, and it is to understand causality. This is not causality. Absolutely, with these methods, you can get the right answer for the wrong reasons. And so this is merely a step in the process, not the step in the process. Okay, so back to our problem. I'm focused on Central North America, and I showed you some base network that was then updated when it saw observations to get this new fine-tuning curve. And the question is, what did it change within the network to get this better prediction? And what we can do is make XAI maps of the teal curve and the orange curve, and then we can take their difference and say, what's different about where the network is looking? And this is what we get. And so we end up finding that there are these regions over the Southern Ocean as well as over Central Asia that are updated in the network to make this better prediction. So these may be places that you might describe as regions where there are relevant climate model biases for this task. Not all biases. I mean, if we really wanted to look at mean biases, we could just take means of things and subtract them. But these are the regions it was important for this task to be updated. Okay, so moving on, in this community, large ensembles, chaos, these things are important, so you can look over temperature trends over many decades and everything's red. But we look over just a decade and we can get very many different futures in the next 10 years depending on how everything aligns. A lot of people call this noise. This to me is why I'm a climate scientist. I love that this picture looks like this. It means it's really interesting to talk about climate prediction even beyond a 2, 3, 4-year timescale. It means even if there's a forced trend in there, actually making a prediction on this 5-year timescale means you have to care about internal variability, which is one of the interesting parts for me. Okay, so I'll click through this part just since, this is NCAR. You guys know all about large ensembles. But again, we can talk about the forced response, but we can also pull out single members and be living in any one of these. For folks, by the way, for folks that are not in the climate and weather community, this sets of slides is mind-blowing to them, okay? We've talked to people in hydrology, in political science who go, wait, it seems like I should care about this. And the answer is yes. Yes, you should, right? We shouldn't just be planning everything in the mean. We have to care about these different members. So we're using AI to constrain future projections by fusing simulation and observations on these longer timescales, as I pointed out, but also to look at multi-year predictability. So would we have been able to forecast or predict this huge drop in temperature over these few decades in this particular member? And the question is, could we do that? Well, we can test that because this is a model run, thankfully. The other thing is, we often talk about prediction like this to prepare for weather and climate hazards, which is incredibly important, right? And thinking about infrastructure, don't get me wrong. But also, we have some new work, especially in our work on stratospheric aerosol injection, so climate intervention strategies, looking at the ability to anticipate the masking effects due to internal variability. So we have some papers out, for example, on thinking about net zero. And if we were to actually hit net zero, and the next year was a really strong El Nino, or the next 2 years were really strong El Ninos, what would that look like to folks that are not Earth scientists? And it would look like, well, it didn't work, right? You told us to do this policy, and it obviously didn't work, and so we're gonna stop. And so being able to predict the next few years of internal variability could be really important to communicate. Otherwise, it could also be masking, again, these intended effects, when in the end, the policy worked fine, right? Okay, but climate prediction is really hard. So whenever I give this slide, people are like, you make it sound really easy. It's very difficult, to be clear. We can't make perfect predictions all of the time, and this is where I really think that AI can be very helpful in thinking about forecasts of opportunity or state-dependent predictability. That is, not all states are as predictable as others. Which ones are predictable and which ones aren't? And can we know it beforehand, right? Looking backwards and going, whoops, that was a bust, is important, but not as helpful as if we could say, this is going to be a bust. So that's where, I'm gonna skip this right. This is where things like El Nino and the Madden-Julian oscillation really come into play, and this is why I really like to emphasize this. Machine learning is beautiful for this because it's really about patterns, which we have so many of in the climate system, and it's about nonlinear behavior, right? And these two things come together with this idea of state-dependent predictability. Okay, so one particular project that I did with, led by Francis Davenport, a former postdoc, now a professor at Colorado State, was to predict ocean temperatures in the following 5 years. In this case, we're going to classify between warm, neutral, and cool, and she's inputting maps of sea surface temperatures over the last few years. You can think of this as inputting the temperature tendency, right? Some sort of delta T of how it's changing. And you need to know, is it going up or is it going down? Just knowing where it is at one fixed point isn't necessarily useful. So she trained her model. It does fine, but I'll hopefully convince you a little bit of that in a minute. This is sort of the overall look. So this is trained on MPI ESM. So she trained on 3,630 years of data, which is a lot, right, to make this 5-year prediction. And this is her overall accuracy. This is a 3-class problem, which is balanced, which means a third is random chance, or 33%. And some of you might see that the banana color looks a lot like 33%. So this looks like it's not working very well. It's pretty sad. Okay, so is this all that we have? And the answer is no. This is where state-dependent predictability comes in. Now what we say to the network is, tell me which predictions you're more confident in, and we're going to take those and look at those specific predictions. And when you look at the 40% most confident predictions by the network, which is a metric you can pull out in this setup, you start to see that you do have skill when the network is confident that it will be right. So this is sort of like the network telling you, hey, pay attention to this prediction, or hey, this prediction's gonna be bad. Or maybe it won't necessarily, I don't know how this prediction's gonna do, right? And if you even look at the 20% most confident predictions, you start to see quite high accuracy. Now, unfortunately, as humans, we don't get to choose when the 20% most confident happens. So if you're trying to plan, this is on climate timescales, but if you're trying to plan, I always use the joke for a wedding and whether to pay out for the umbrellas for rain, right? You'd have to hope that you got lucky and you were just entering a state-dependent, highly predictable state, and we don't get to choose that. Okay, this is on climate model though. So this is a climate model predicting itself for the left out data. What about observations? So we used exactly this same network here and applied it to the observations. And on the far left, if you look at all accuracies, it looks pretty terrible. But if you look at when the network was more confident in its predictions, we actually do see regions of the globe, especially the North Atlantic here, that are far more that are actually show skill. And once again, we can use XAI to say how is it able to identify when there's predictability and when there isn't. So what is it looking at? So in a similar way, this is almost the same problem, but a different paper, where we're looking at 5-year predictions based on sea surface temperatures, but we're going to predict land temperature anomalies. Once we've done that, we can use XAI to go backwards and say what part of the sea surface temperatures were important for this prediction. And we can make maps that look like this. So these are those cat heat maps, but instead of cats, right now we have an actual globe. And what's fun is for different regions of the globe, for different predictions, different regions of the ocean pop out as important in having information in them, right? But on top of that, even for the same location, different time periods, the network is looking in different places for that predictable signal. And we as scientists know that in one location, it's not only influenced by one phenomenon, but there are multiple things that end up feeding back to lead to predictability. Okay, so as I said, we've been using this explainable AI methods to explore Earth system predictability, not just multi-years in advance, but also days to years in advance. So thinking about sub-seasonal timescales. And I could show you a bunch more papers of heat maps and great work that people have done on this. I'm going to take a slightly different detour and just talk about these emulators, because that's where a lot of things are happening right now in the field. So this is ForecastNet version 2. So on the left is the AI model out of NVIDIA. On the right is their ground truth, in this case, ERA 5. And I will say, just from the big picture, it's absolutely mesmerizing and beautiful. It's amazing that this works. And there are folks here developing similar types of models. These models are here. They're, I don't think, going anywhere. And so one question is, how can we best use them? How can we best evaluate them to figure out when they fail and when they succeed? Also, I will point out, these have been around for a few years now, but we've seen accelerating improvements in the last about year and a half, where models now are starting to fight for tiny little differences in how good they are up there in that box. All right, and I will point out, to date, most of these that you've heard about are weather models, but they are not all just forecasting or weather forecasting models. There are, in fact, moving towards climate models, and in recent months, folks are actually coupling atmospheres and oceans together to get coupled AI emulators. So we are months away, I think, from really starting to see those become usable. So in this case, this is just an example of neural GCM out of Google. By the way, if these look fun, this particular model, you can just go on Collaboratory and run yourself, which is pretty cool. I actually taught a class this past fall with Russ Schumacher in my department, and we did data-driven forecasting from hours to decades. And students were able to run multiple emulators just on their own laptops or in Colab. So if this is something of interest, I wouldn't say it's too easy, but we're getting close to, like, anybody can click a button and hit go on these things. One of the things, by the way, just as a side note, that makes this pretty neat, you might note the phrase dynamical core in there. This is actually a hybrid model where they actually do have Navier-Stokes, but then they're using machine learning for the learned physics. That's a bit different than the fully AI, everything's machine learning. Okay, so I have multiple people in my group right now trying to think about these weather emulators for sub-seasonal prediction. the idea is they weren't designed necessarily for this, but how do they do on these timescales, and can we start to learn where their strengths and weaknesses are? Even since starting these projects, a lot of the industry has started turning their eye towards S2S. So I will point out in the last 6 months, I've seen many projects spinning up at different private companies on this topic as well. So expect more in this space. So I've talked briefly about the Madden-Julian oscillation, and one question is, how do these AI emulators do at the MJO? Because this is really important on subseasonal timescales. So work by Shen Ray and a postdoc in my group is actually, this is near and dear to a dynamicist's heart. Let's go in and put idealized heating into the emulators and see what happens. This sounds a lot like an LBM or a linear baroclinic model, only it's nonlinear. And it has much more than just the baroclinic piece. So he has gone in, put in idealized heating that mimics the MJO, and we're looking for geopotential height responses that look PNA-like. And this is an example of one from the AI Pangu weather model. And it looks okay, actually. There's a lot more work, obviously, behind all of this, but it did better than we thought. Kelsey, a master's student in my group, has been interested in heat waves. And here's an example of the June 2021 North Pacific heat wave. And the question is, how do these AI forecast models do at these extremes? There have been multiple papers on individual events, and what Kelsey wanted to do is go in, and she's collected over 60 different impactful heat waves over the US to see how do they do. One of the reasons we don't know the answer is because these models are largely trained on root mean squared error over the whole globe all of the time, and by definition, these are extreme events. So how do they do? And if they struggle, one of the things I find exciting is how do we tweak their training to try to do better at these tails? Here's just an example of this particular heat wave, showing the observed. GraphCast is another Google model, and then this Pangu model. This is just one case study, but I will tell you something we found is that the Pangu model in this case was often too cold. GraphCast was also biased cold, but not as much. Now the cold makes sense because, as I said, these are extremes and they're trained to do well on the temperature all the time, right? So it's perhaps not surprising, it's not surprising that if they're gonna be biased, they'll be biased cold. We're also using, now this is the ACE climate model. It's called the climate model. It's not coupled yet. It's really an atmosphere only model, but actually the Allen Institute group led by Chris Brotherton is actually working on their coupled version right now. So it will soon be their ACE climate model. And what Muting has been looking at quite a bit in my group is she's studying tropical cyclone formation and genesis in these models. Does it behave the way it should with the surrounding environment? And if so, can we then use it to ask climate questions about TCs, but where we can run thousands and thousands of years that simulate TCs in a matter of a few days. So this is really exciting. Okay. And then finally, work that I'm doing with Maria Rugenstein and Senna Van Loon is thinking about how sensitive is the real world. We'd like to know sort of that Green's function, how sensitive is the real world top of atmosphere radiation to sea surface temperature anomalies. So if you've heard, you go in and you heat a little blob, and you run a climate model out, and you see how the TOA responds, and then you start a new simulation and you put heating in another little set of grid cells, and you do it again and again. That takes a lot of time, and folks have done it, which is great, which means we sort of know the right answer in those models. And now we can look at, in this case, the ACE climate model and say, how does it do at getting these sensitivities? And on the left is the AI model, and on the right is the physics-based model. And while you'll see this, the colors are much weaker on the left, right? It's not the same. The pattern's pretty similar. And again, not only did we not expect this, but in an earlier version of ACE trained on the NOAA, one of the NOAA models, it did not get the right pattern. This particular version of ACE, though, was trained on ERA 5. So a closer realization to sort of reality. So anyway, this has been really fun. Okay, so in sort of transitioning to the final part of my talk, these emulators, I'm throwing things at you, but I think the big picture here is how are we going to improve these models as they fall short? The time of just getting excited that they're running without exploding is coming to an end. And we're going to start to get picky about things like heat waves, right? Things, impactful events. And how will we start to improve them? And I think just like with climate models and weather models, that's really hard because we're interested in emergent properties of these models, not just the individual grid scale behavior. So that's going to be a place I think that the academic community has a lot to offer. How do we leverage their power if they succeed? A lot of people come to the mindset of let's just do everything faster and cheaper. But let's get creative and think of questions we couldn't have even asked before had we not had these tools. And again, that's going to require physical knowledge of the system. And then finally, how do we understand their decision making? And I think, especially given the XAI piece of this talk, this is really challenging. It's actually very hard to do some of these explainability techniques with these emulators. But people still want to understand how they're coming to the conclusions that they are. So with that, I'm going to transition to, instead of trying to compete with the Googles and the Apples and all the others, the Microsofts, we're going to take a different approach. And instead of trying to explain the emulators, which I'm fascinated by and have some work that I want to do, we're going the other direction, which is how simple can we make some of these things and still get pretty good answers, okay? And this world is called interpretable AI, or the idea of actually building AI models that think like we do. And I don't mean that in the creepy robot sense, but what I mean is we set them up to approach the task and use the information we as scientists think is important to ultimately get, hopefully, a good answer, as good of an answer as if we'd use the more complicated method. So there are now quite a few papers on this topic, but this is an old paper by Cynthia Rudin, and what I really like is it shows the left, it pretty much shows you how my cat heat map has lots of problems, okay? What it says is here's the test image, in the middle is that heat map for where it's looking to determine it's a Siberian Husky, and you're like, ooh, it's looking where the dog is, this is great. But then on the right is where it's looking to know that it's a transverse flute, and you're like, oh, it's also looking at the dog. Which on the one hand makes sense. It should look at the dog to know it's not a flute. On the other hand, as a scientist, if it's always just pointing to the same place everywhere, we've lost sort of the whole point of explainability. All right, so I just in the end here want to talk you through what one of these approaches that we have taken. And I'm going to come back to this figure, but one thing I want to note, and I've talked to my CS friends about this for a while now, is when a climate scientist or an earth scientist looks at a map of sea surface temperature, precipitation, whatever it is, your favorite variable, our eyes automatically start going to specific places within that image. It could be where we live, it could be the region we're studying. If we're about to make a subseasonal prediction, I probably will look in the tropics to see what El Nino is doing and the MJO. I already know to look there. So one of the ideas is, can we build models that do that looking as well? If you've heard of attention mechanisms and transformers, this is exactly the same idea, but we're just trying to simplify it as much as possible. All right, so this is a famous paper by Ed Lorenz in 1969, talking about chaos, but instead of chaos and analogs, if you've heard of analog forecasting, this is one of the oldest ways we've been forecasting weather for a long time. And he talks about naturally occurring analogs, that is using observations of the past to help us understand what the future might hold. But we actually don't have that much data from the past, especially on some of the longer timescales that I study. And so instead of looking at the actual past, we're going to use climate model output to help us find situations that look like right now. So the idea is, imagine this is our state of interest. Imagine for example, this is today. This is what sea surface temperatures look like right now, and we want to make a forecast. Well, we can go back in time, forward in time. We can look at the now time in a lot of climate models and look for cases that look like this map. And the idea is, if it looks like this, they might evolve in similar ways. By the way, if you're confused, there's no machine learning yet, okay? So, just in case. All right, no machine learning. This is good old-fashioned analog forecasting. So imagine we go, okay, those are not very good analogs, but those two look pretty good, okay? And what we can then do is say, well, how did these states evolve into the future? And we can use them to make an ensemble of trajectories of what we think could happen in our current state where we are right now. All right, so we're going to do this. Let's use, for example, sea surface temperatures over the past 4 years to predict the future North Atlantic SSTs, for example. So this is a multi-year forecast. What I'm going to show you first is a perfect model application. So we're going to use the MPI model to both do our training and find our what we call our library of analogs, and then we're also going to withhold some members and pretend they're the real world and then see how we do. At the end, I'm going to show you some observation pieces, don't worry, but we're going to start with the easier problem. So the big thing with analog forecasting is we have to decide what a similar state looks like. We have to go into our library and find states that look like today. I might have glossed over that. What does look like mean? And when I ask students that, they'll be like, well, they look the same. And I'm like, how? Right? Is their difference small? Did you square it? Is it root mean squared? Is it absolute value? Are you looking everywhere? Well, no. We don't care about that part of the globe. Well, how does it know that? Right? So sometimes what people will do is they'll go draw a box and they'll say, well, I already know it's this region that's important. So they need to look alike in that box. And I'm like, okay, but you had to know that box was the right box ahead of time. So the big idea is here, we are going to only use machine learning to help us identify where to look when we do our matching, when we do our look-alike. But otherwise, we're going to do pure analog forecasting because we understand that process. It's explainable or interpretable. And we will understand the full decision-making process from then on out. So the next plot I'm going to show you is a little scary. We don't need to walk through it, but it'll be there for questions. So this is the actual approach. But what I want to highlight, so what we're actually doing is using a neural network. So there's a neural network buried in here. But really, all we're trying to learn is what we call a weight mask. And it's literally a mask of values between, if you will, 0 and 1 that tell you which regions should be more important for matching and which regions, if they're weighted at 0, it doesn't matter if they match or not, we don't care. Okay? That's all we're learning with machine learning. So you can imagine here's a weighted mask and it's telling you the blue regions they need to match in these locations, and the white regions are saying it doesn't. It just doesn't matter. Okay. So as an example, here's one of those learned masks for that prediction problem of predicting the North Atlantic SSTs in the coming years. Okay, and you'll see the majority of regions that pop out are the regions in the North Atlantic, right? Off of Greenland and just off the east coast of the US. And so when we go to identify analogs, on the left is our state of interest, what we're actually, so this is, if you will, today. And on the right is the best analog we found in our whole suite of our big library, okay? And now you might say, okay, those sort of look alike in some places, but in other places, you know, they look a lot alike here, but they don't really look alike at all in the Pacific. How could this be the best matching choice? And the answer is because when you apply this mask, the Pacific just doesn't matter, okay? The best match is really in the North Atlantic, and when you do this masking, you find they look nearly identical in the regions that our machine learning algorithm has identified as important. And then we can use these best matching analogs in the similar way to just make trajectories and say, what did they do? And this is our forecast. When we do that, we get something like this. So the truth is in blue, and in black are our top 10 analogs. And I guess you're supposed to get, they sort of go up and down together to a certain extent, okay? But furthermore, what Jamin went and did is he showed that for particular predictions over the recent decades, this weighted analog approach using the MPI climate model for the analogs, by the way, specifically, so that's our library, did about just as well as the CFS version 2. Training this network is actually very cheap. This is not a deep network, so getting that mask is relatively cheap. And then running our forecast system is merely going and finding who has low RMSE, and thus we have a forecast. Another thing I really like about this approach is when you're explaining it to someone, it is analog forecasting, period. All that the machine learning is doing is helping us choose which analogs to grab. And right, and I'll show you another part about it, which is allows us to start to look at sources of predictability. Yeah. So what's neat is this is still one of those masks, but this is for a slightly different task. He was predicting El Nino. And do you see how different regions really popped out? We can then play games where we remove them and keep them and see how important they are for the final prediction. So in a way, we're also doing explainability, but in a way that makes sense, sort of this leave one out perspective. Martin Fernandez, a research scientist in my group, is now taking this further, and he's saying, why just the MPI model? Let's use all of our climate models. That seems like a better idea. Then we have a lot more choices. And we're using this to take projections that were run for CMIP6 and turn them into initialized predictions. And that's the part I get really excited about, is we didn't need an initialized prediction system to create initialized predictions with this analog approach. I'm going to skip that one. So he's applying it to many different tasks over multiple multi-year timescales and getting different masks, which regions are important for different predictions in different parts of the globe, we get different answers. Furthermore, we can take this and actually make, in this case, years 5 to 7 surface temperature anomaly predictions over the western US and compare them to the full CMIP range, which is not initialized, right? And this is they're not meant to be used as a forecast. I know this. But we've taken that blue uncertainty and constrained it now with our initialized forecast system of analogs to the yellow. And that was the goal. And finally, I want to point out, I haven't shown these results, but you might say, yeah, but what if I just used the whole globe and matched on the whole globe? Like, I could have done that. Now, if you have an infinite library of states to choose from, that's the best option. Because you have an infinite library, you will find a state that looks exactly like today everywhere. Okay, but we don't have an infinite library at all. So instead, this mask is helping us really refine where we are looking for those best matches. If you did use the whole globe, that's our global mask. And if you used a regional mask, that's you just going and drawing a box in a place that seems like a good idea and seeing how you do there. And the point is our learn mask does better than these simple alternatives. And furthermore, it's actually, in this case, we have two initialize Earth system model decadal prediction systems, and it is beating those as well. So I'm going to wrap up now. We made it after lunch. Rough time. All right, so I like to zoom out at the end of my talks, and instead of telling you, here's the 5 facts I want you to take away, to be honest, I never take any facts from any talk. I'm surprised if I remember who was talking at all. So just really big picture. I think the future of Earth system, human Earth system science and prediction is going to obviously, maybe this is obvious, but we have to do interdisciplinary thinking, right? That doesn't just mean the atmosphere talking to the ocean, but that means economics, policy, right? Computer science and statistics. We really have to integrate this even more. But ultimately, as we do this process, not only will machine learning, I think, help us talk to each other, but it will help us ultimately ask the question of why. And so with that, thank you.
All right, thank you for that brilliant talk. I think that will lead to a lot of questions. We'll take questions from online and in the audience.
Thank you for your talk. I got excited listening about analog. And no, I'm just, as a general comment, so my understanding is that you look back at an archive of thousands of simulations from a climate model, you find the most similar. But then, so that means, so I have 2 comments. One, you still rely on the fact that the climate model is accurate, because then you look at the trajectories of the model, but those might be wrong.
Totally.
So that's the first comment. The other comment is that for predicting future climate, you're going back to years in which there wasn't the climate signal. So you're trying to learn from the model in the past where there was a different kind of environment, in terms of climate signal. So how can you rely in the future for those past trajectories to be reliable?
Right. So actually, I'm going to address your second question first. So actually, we're training on, our library includes all the way up to 2100. So we're not just looking backwards, we're also looking forwards. And actually, we have a figure that shows what years is it choosing in the climate models when it makes predictions for today. And we can actually address the question of maybe it's grabbing 2045 maps, even though right now it's only 2025. So that brings me, however, so I think that part is not so much an issue, but that brings us to the very important point.
Sorry, but
Yeah.
still in 2045
Yeah.
there might be a different global. So all the effects are not linear. So
Agreed.
the analog from 2045 might be not the same.
Totally. Yep, and that's where the neural network comes in. First of all, it's helping us learn a mask that works across all these timescales. We also are developing tools that are state-dependent masks, and this is where we start to lose the beauty and simplicity. But you can imagine with a neural network saying, when it sees a certain pattern from a certain year, realizing that it needs to use a different mask for matching than in another year. So that isn't currently in this system, but rather because we're training it over maps from 1850 to 2100, it needs to learn the regions that are reliable across all of those decades, not just a few. But that brings me to your first point, which I think is really important, which is this assumes the climate models are right. And I think this is yes, it does, except, okay, so yes, to a certain point. I didn't show work here, but that transfer learning idea that I introduced earlier in the talk, where once we've trained a machine learning algorithm, we then update it with the bit of observations we have to make it more relevant to the real world, in essence acting as a bias corrector to a certain extent. We're doing the same thing for this mask. So for this analog mask, where we train on our climate model library, but at the end, we fine tune that mask to make it updated for the real world. This shouldn't be seen as going from here to here, but more like a Taylor's expansion where we're at X naught and we're just going to deviate ever so slightly from that. And we have found that transfer learned mask does in fact give us better results on our real world samples. It's not a fix though for all of it, to be clear. Yeah.
Thank you.
Thanks for a great presentation. My question kind of ties to the past one, but it's more on the SSP and how it is applied. SSP assumes a homogeneous practice across the whole world, versus your recent data would consider how different parts of the world are applying different practices, the population is different. So how you see the impact of that and what can be done to correct
so this
that?
doesn't address that at all. Full stop. So I could end my question there. We're done. However, I guess few answers to this. One of the things I'm excited about is our general approaches seem to work. And so as new simulation types, et cetera, come online, this should become more plug and play. And I'm excited about, because really what some of these methods are doing is they're like a weighted modeling scheme. Like I know I use the word machine learning and explainable AI, but at the end of the day, what is it doing? It's weighting patterns and models and deciding what combination is best to get the lowest loss. That should be applicable no matter what scenario and version you're using, okay? The second thing is, one of the things I'm excited, this is a big grand idea, by the way, and I'm not working on it yet, but I would love to, is trying to incorporate more human actually responses and decision-making into climate models, which I know folks at NCAR have talked about, but that's really hard. And it's potentially going to be very slow, because that can be, if you're doing it at an agent-based scale, this is going to be incredibly challenging and difficult. I'm very excited for the ability of the machine learning tools and AI emulators to allow us to speed up the climate part enough that we could actually play with incorporating the human component in there as well. So that's different from my projection work, but just saying I think the machine learning may allow us to start to attack those and actually get to real results much faster than we would have if we'd stayed with more traditional dynamical models. So, yeah.
Thank you.
I grabbed it. Yeah, this was really great. It was very different than what I expected. And yeah, I think it was a great presentation. Thinking about how, like, if you use AI to do some kind of prediction and it identify the reason for that prediction as something that we have not considered, how often is it a bust? Or actually something that we should be looking into?
Yeah, great question. I do not have the number for you, the percentage. So this comes up a lot in computer sciences, the explainability literature, because we have what's called confirmation bias. If it shows us what we expected to see, then we go, oh, good, everything's fine. And then we move on. We trust it now. If it shows us something we didn't expect to see, most of the time we go, oh, there must be something wrong with it. And we'll often tweak it until that thing goes away. All right? That whole process, at least to my knowledge, nobody's figured out exactly the right way to do it. In our work, and this is where my subjective judgment comes in, I look at these heat maps and I'll say, oh, okay, that's ENSO. Oh, that's probably the MJO. Oh, I wonder what that dark blob is. Let's look into that. It's typically real in the sense that, yes, it is useful to make a prediction. The question is, though, is it tightly coupled to, say, ENSO or the MJO, and really I'm just getting an after effect, in which case it's not causal, but it is like a source of predictability. And typically you'll see, so even in some of the analog masks, not everywhere is perfectly white, but my brain is automatically going, oh, let's ignore that part. And so actually I'll just show you quickly in one of these, this mask here. One of the things we did is we said anything that was below the 95th percentile of color, so it's almost everything in this plot, we're going to zero out. Because if it's actually important, it should make the prediction worse. It doesn't. It's about the same. What that means is that's our noise level. And so if I sat here and analyzed every single thing that wasn't zero, I would be wasting a lot of time. And so that's why I have colleagues that frame this more of hypothesis generation. And then what we have done, I have worked with a graduate student of Maria Rugenstein's who actually did this process and then went into a climate model, a physical dynamical climate model, and tested how important that one region actually was and showed it was critical. So in that sense, there's still more work to be done, but as scientists, we already know the experiments to do to test them. So, yeah.
Okay, so we are at time, so if anyone has to leave,
Go ahead. Yeah.
feel free, but we do have a couple burning questions I noticed, so I'll let these last two. Chris and I. Pat?
You're torn.
So this is kind of a philosophical question, because when I think about this, it's like, in my simple thinking, like this is kind of a sophisticated way to do statistical downscaling. And the weakness therein in statistical downscaling is the underestimation of the extremes. But when you're talking about, well, at all of these forecast timescales, which you summarized, that's really, from a societal impacts perspective, what we want to get at. So are we ever going to have enough training data, whether it's observations or models, really to get at this question, or is it some kind of creative combination of physically based models and AI?
Yeah. So I think right now the community has identified that these extremes are really hard, which we knew, but that many of these AI models like to smooth things because it's a better way to optimize the problem. But there are new approaches, for example, diffusion modeling and generative modeling, that do not have these problems. So in the last year, we've seen that, oh, wow, there are techniques out there that can get the details to really high resolution fidelity without the fuzziness. So my answer for you is give it another 1 to 2 years, and I don't think it's going to be solved. To be clear, I think this is so many fun research questions to ask over our lifetime. But I think it's not well, that was a shiny, cool tool, but it's not actually getting what we care about. I think the opposite. I think this is going to allow us to continue to make progress, but we're going to have to do it very intentionally and carefully. And we're going to have to think about, how do we train it the right way? How do we emphasize the tails when they're the most important? How bad is this smoothing? I have a student thinking about that. Like, when we say it can't do extremes, like, where does it stop? Right? These are questions we don't know the answer to yet. So I'm optimistic.
Yeah, and don't take that as a criticism.
No, not at all.
I just like,
Yeah.
when do you get it to the point that you have confidence to say it can forecast that heat wave?
Yep, and we don't know that. We're working on that, and I think this is where the community using these emulators is really powerful, because there aren't enough people yet looking at them. Okay, sorry.
Okay, I did promise Pat a quick
Okay.
question. Sure. Okay, and then we have to wrap it up.
Yeah. Nice throw.
Why was it looking at the sea ice? I was
Oh, this
the
was a
same
tot-
question
yeah.
as Maria, but like why was it?
So this was a totally different problem that I have not shown you here, but in the end, I think the sea ice was an indication of what year it was. Because sea ice is such a function of like the climate response, whether there's ice there or at all or not. In this case, it was annual means of things. And it wasn't even looking at sea ice, it was actually temperatures, but you can tell where the ice is. And we realized, the reason we didn't want to look at ice, I realize now I offended all my ice colleagues. It's that it was such a clear signal. This is why I love machine learning, but often people decide they don't like it, is because it cheats, but stays within the rules. So you give it rules, it does not go beyond them, but it will find the sneakiest way to follow those rules. And in this case, it was pretty much like, I know what year it is because I see there's no ice there, and that's not what we wanted. Yeah, cool.
There is an online question as well.
Okay, so this is from Anish Subramanian. It's a great talk, thank you. How can we use your XAI or IAI results to improve our current dynamic or hybrid models by correcting their errors in data assimilation systems?
Yeah, I mean, this is a huge question. I mean, like, Will Chapman was just at CSU yesterday and gave a talk and talking about learning these increments, right? And that these increments really can ultimately grow to these much larger timescales. And I think at least that work to me is incredibly exciting and powerful. And I suppose the XAI piece, which even I want to give him full credit, I think he even mentioned, was saying, okay, I see these increments are being learned. Why are they being learned? What about the current state is giving the increment, making the increment that big that the AI model learned? And you could use XAI to then go and say, hey, I think it's the boundary layer scheme. And yes, that's a direct quote if Will is listening to me. So anyway, so I think there are answers and there are people here working on them right now.
All right, we have to wrap it up. Let's thank our speaker for an excellent talk.